Let's consider the satellites or moons of the planets, in particular in the outer solar system. The exploration of these moons is one of the pinnacle achievements in the space program. Iapetus, small moon of Saturn, is just one example of the moons that Cassini has visited up close during its decade-long sojourn in the outer solar system. The key insight of the last decade is the fact that the moons in the outer solar system are not boring, frigid, geologically dead worlds. Many of them have atmospheres, geological activity, tidal heating, and are interesting and distinctive worlds in their own right. Based on current planetary models, as many as a dozen of the moons of the outer solar system may have liquid water, kept liquid by pressure from rocks and ice above and heating from the interior. This means that there's more to the outer solar system than meets the eye. If we look at images of these large satellites of the giant planets, they look uninteresting. Cratered surfaces of rock and ice, scarred by cosmic rays and ultraviolet radiation, not even possible for habitability. But under the surfaces, interesting things could be happening. Perhaps the biggest surprise came a few years ago when tiny Enceladus, barely larger than Rhode Island, only 500 kilometers across, was shown to have liquid water under its surface that episodically spouted ice particles as frozen geysers out into deep space. If we look at the comparative sizes of the largest moons of Jupiter and Saturn, we see that they rival Mercury or Earth's moon as significant astronomical objects. Since radioactive heating is strictly proportional to the mass of an object, these large moons or satellites have substantial internal heating, which can, in the extreme case, help lead to geological activity and even volcanism. So if we compare a terrestrial planet or terrestrial object in the inner solar system of the same size as a large moon in the outer solar system, there are extra ingredients in the outer solar system that make those objects interesting. One is the radioactive heating that goes with their size, but a second is the tidal flexing that goes with being in orbit around a large planet. Tidal heating comes because the orbits of the moons are rarely circular. As they move to their closest and then their furthest distances, they're squeezed by the planet, like a racquetball or a squash ball might get warm if you squeeze it over and over in your hand. This tidal heating can be substantial, can even rival the heating that comes from radioactive decay naturally in the rocks. These two effects combine with the fact that icy material is more viscous or supple or pliable than pure rock, which means that taken together, the outer solar system is an interesting place where there's the possibility of geological activity, even though it's very far from sun and surface temperatures are hundreds of degrees below zero. Two examples of this are Ganymede, the largest moon in the solar system, as large as Mercury, which has a cratered icy surface that almost certainly overlies an ocean, perhaps hundreds of meters deep, and Callisto, a similarly cratered world in the outer solar system that may also have a deep buried ocean. None of this is visible from the surface. It must be inferred from reflectance spectroscopy and inferences of the density profile interior to the surface. All of this is important for the potential for biology in the outer solar system. Really, all that we know is that life needs energy. That energy doesn't have to come from a star. Life doesn't have to exist just on the surface of a planet at the appropriate distance from a star where water can be a liquid, not so hot that it boils, not so cold that it freezes. The conditions for liquid water can easily be maintained within a moon or a satellite very far from the sun, from these local heat sources of radioactive heating and tidal heating. What we've realized in the last decade is that the real estate in what's called the cryogenic biosphere, far from the sun, where ostensibly the temperatures are below the freezing point of water, that habitable real estate could vastly exceed the habitable real estate of rocky bodies in the Goldilocks Zone, where the Earth is, and liquid water can sit on the surface of a planet. This in turn means that if we only look for life on the surfaces of terrestrial planets close to their stars, we may be missing most of the sites in the universe where life exists. Even then, our thinking about life is necessarily bounded by what we see on the Earth. Astrobiologists have speculated there might be life in even more extreme environments, keyed perhaps by an article, only partly tongue-in-cheek, by Carl Sagan and Ed Saltpeter in the 1960s, speculating that there might be buoyant jellyfish-like organisms living in the upper clouds of Jupiter. The temperature profile of the Jovian atmosphere is such that the outer regions are extremely cold and the interior regions extremely hot. But there's a temperate vertical zone where in convection currents it's possible that it is indeed habitable. Other planetary scientists have even speculated about life on Venus, which we think of as a toxic inferno. Again, there are upper regions in the clouds where the temperatures are temperate and between the freezing and boiling points of water. Even more extreme as a possible place for life would be Io, where the complex biochemistry would have to be based on sulfur rather than carbon. Nobody has any idea if sulfur-based biochemistry is even possible, but the premise here is that chemical dynamism is a prerequisite for life. In that sense, Mars may be mostly dead because it's not a chemically very dynamic place, whereas the little moon Io of Jupiter, which is kept volcanic by tidal heating, is an extremely chemically dynamic place, leading to the speculation that it might host biochemistry of a strange form never seen on Earth. Also, life on Earth provides us with the lesson that biology does not necessarily need the warming radiation of a star. There are ecosystems below the ocean's surface, under extreme pressures and at extreme cold or hot temperatures, that exist essentially independent of the sun's radiation. The source of their energy is geological, and those geological sources of biological energy exist elsewhere in the solar system. And these are not just simple microbial life forms. Entire ecosystems of life, ranging to large creatures, exist near subsurface volcanic vents on the Earth. Of course, continuing this logic, it's entirely possible that life doesn't need a star at all. Perhaps there are planets free-floating in space, having been flung out of their solar systems at birth or after, which are able to harbor life. The moons or satellites of large outer planets are interesting worlds in their own right. They have extra sources of energy compared to similar objects in the inner solar system. That energy could potentially support biology. And it turns out that the cryogenic real estate for life at places where the surface temperatures would be far below the freezing point of water probably vastly exceeds the terrestrial real estate in a world where water can be liquid at the surface, the so-called Goldilocks Zone.